Okay, so today we're going to start something called verifying identities. And verifying is proving. Okay, now do you remember proof in geometry? Nobody really loved, well, you might have liked proof in geometry. Every now and then there's somebody who's like, I don't really like this. But a lot of people are like, I feel like I'm saying what's obvious. You know, I feel like I'm saying these statements and like, duh, of course they're statements. Like, why do I have to say opposite angles are congruent or alternate interior angles are the same? Why do I have to keep saying that stuff? We know this stuff. It's kind of like A equals A. I took a proof class once. Worst class I've ever taken. And literally day one, we proved that A was A. Then we proved that A times B equals B times A. I mean, you think about it, you know these properties, right? A times B is B times A, or A plus B is B plus A. You know these, but there's a proof to them. And it's not cause, or of course it is, duh. You can't say that. Well, we're going to be proving or verifying identities. And the form that you use is important to me, okay? Now, unfortunately, in your book, if there's bookwork, their form is not important to them, but it is to me. So if your form is bad, you're going to lose points for bad form. Think of it like, I've got two examples. There was this dude from South Korea, I think it was, in the Olympics a number of years ago, and he was a butterflyer, and he was the best butterflyer. I want to say he did the, might have been the 200 butterfly. So I think on the 200, you got a 50-yard pool or 50-meter, 200 meter. So it was a 50, every 50 meters, he does this little flip turn. And in the butterfly, you know, I don't know if you've seen the butterfly, but you're doing this really awkward stroke, right? Well, the guys, when they push off from the wall, you're allowed to go underwater as long as you can hold your breath. You can just kind of do this little scissors kick or whatever, not scissors, but this little like, I call it The Man from Atlantis because there was this dorky show back when I was a kid called The Man from Atlantis. And they would show him doing this little swimming thing underwater all the time, whatever. But you do this little thing underwater, and then when you finally have to surface, which a lot of these guys don't even surface until halfway across the pool, right? They surface, and then they start their butterfly. Well, that's okay to do that, but this guy was 10 yards ahead, 10 meters, whatever ahead, way ahead on his way to the gold medal, final round. He does his last kick turn, right? And he does the little thing, he gets to the wall, and all of a sudden there's this red flag that goes up, and people are, what's going on? And one of the other underwater cameras caught his feet. Now, your feet are supposed to stay together on the butterfly. If you're a swimmer, you know that, if you do the butterfly. And his feet, you're allowed to kind of separate a little bit. But if you do a scissors kick, a full scissors kick, you are DQ'd. And they went to the tape, and they looked at it, and he did a full scissors kick, and he was disqualified. Now, that scissors kick didn't help him that much. It just happened one time, DQ'd. Out of the race, no gold medal because of what? Bad form. Nice. I never get that answer so quickly. All right, he had bad form. Form is important on trig identities, okay? Now, some teachers are going to make it harder on you than me, okay? Some teachers say, like Miss Rouleau, for instance, when she taught this class, she would say, all right, we're going to prove this identity. She said, pick one side and just work with that side only. So they had to choose which side they wanted to deal with, and they would pick it, and then they would keep manipulating it using the identities that we already have proven. Our list of identities has already been proven. We can use those. These, not necessarily. So you can use these identities to make the left equal the right. I'm not even going to be that strict. I'm going to let you work on the left side if you want, and if you get kind of tired or lost, you can stop, maybe play around with the right side, which is especially nice when you have like a bunch of junk on both sides. If at any point you can make the right side equal the left side, well, if they're equal, then isn't that the same? And if they're the same, isn't that an identity? We've been saying from the beginning, an identity is when it doesn't matter what you plug in for X or for theta or whatever, you get the same thing. Well, if you can make the left side and the right side equal, then you know it's the same thing. Now, how do you disprove an identity? Like, what if I play around with this sucker all day long and I cannot make it match? And I'm like, man, I don't think this is an identity. How could I disprove it?
You find something
And I only need one, right? Because if it's an identity, it would work for every possible value of theta or whatever x. It would work for everything. So if you get to the point where you're like, I don't think this is an identity, pick any x, plug it in the, I would plug it in the original because you might have made a careless error. All right, plug it in the original. If it's not equal, then it's not an identity. Now, I probably wouldn't do that at the very beginning of every problem because most of these are going to be identities. And on your test, I had a poor soul come up to me once. He's like, ha ha, hands me the test. And he's like, I see what you're doing. I'm like, what are you talking about? He goes, caught all 4 that weren't identities. I was like, well, that's unfortunate because they were all identities. And he's like, oh. But he never checked the value. He just couldn't get anywhere and went, oh, I'm out. So on a test, maybe 1. And I say maybe. Most of the time, I don't even like to put a non-identity on there, but every now and then I'll make a careless error or a typo, and that kind of covers me. So it might happen, but most of the time I get to my test, I make the key out, I proof it ahead of time. So expect them to be identities. But if you get stuck and you're like, man, go back to the original, plug in something like 30 degrees, simplify it, see if it's true. And if it is true, that doesn't mean it's still an identity because you can't just check one thing and say it's an identity, right? You got to check all things. So the best way to check all things is just make the left and the right side equal. So here are my general rules for trig identities. And I put them up here. The lady with actually a really sweet woman, but she can just she just looks normal and then she goes, gunk, and her eyes like shoot out an inch. It's really quite fascinating. And I've seen her do it on an interview. I mean, they are really sticking out. We have time, I'll show you. But anyway, here are some guidelines for proving identities. Now, it's a little like simplifying. You know how when we were simplifying, the big difference was it wasn't an equation. It was just one little part. And I was like, hey, guys, this looks really ugly. Can you use identities to make it look a little bit more simple? You've already got rules for that. Proving your sole goal is not to simplify. It might look worse in the end than it did in the beginning, although most of the time it doesn't. But your goal is to make one side equal to the other. But here's what you can't do, all right? What you're allowed to do is simplify one side at a time. Now, hear this. This is not an equation. I am not allowed to use all the rules of algebra. I can't look at this thing and go, oh, it's an equation. Since an equation, I can multiply both sides by something. Can't do that. The equal sign is more like a question mark. Are these equal? So you can't treat them like an equation. We're deciding, is it an equation? Is this an identity? So you can't go in there and go, well, what if I multiply both sides by sign? Then I can cancel sign. Can't do that. What if I add 3 to both sides? Can't do that. You can't do any of those rules of algebra. You have to think about that equal sign in the middle like a big question mark. Is this side equal to that side? And you can simplify one side or simplify the other. I normally start with the ugliest because there's the biggest and the ugliest has more simplifying I can do. It might be easier to make a match. So I can play with the left, I can play with the right, but I can't do something to both like you do when you're solving. Does that part make sense? Because if you do that, it's the easiest way for me to go, all right, he doesn't know the rules, she doesn't know the rules, and just cancel it, count it wrong and move on to the next. All right, next thing. What you're going to be doing is looking for opportunities, all right, to use your identities to simplify one side or the other. And it says, again, notice what is given on each of the sides so you can see which direction you're headed. What I'm saying by that is, if you look on the left side and there's no denominator, and you look on the right side and there is a denominator, then either I need to find a way to get rid of my denominator on one, or I need to go to the other side and find a way to get a denominator. Because again, I'm trying to make them match. So sometimes by looking at the other side, we get a glimpse of where we're headed on the left or vice versa. All right, next thing. When we're verifying and proving an identity, we don't know if it's true. And if we don't know if it's true, the rules of solving, that's algebra, such as multiplying by both sides, it's not allowed. Again, think of it as 2 separate parts. You're trying to make a match, and the equal is just a question mark, okay? And then last thing, don't just sit and stare at the problem. I always have people that look at this and they're like, ugh. So don't do that. Think if there's something you can do to change one side, try it. And then also know that your answers aren't going to match mine. Your process isn't going to always match mine. I've seen some really brilliant, clever processes students use that make mine look terrible. Like I'll be doing something, I'll get done, a teacher and a kid will go, couldn't you just say blah? And I'm like, oh, that's so much better. Well, it's the opposite's true too. You might, take you might take a different approach to get there than I would, okay? That's totally fine as long as your math is right. I've seen people make like 6 errors and then get to where they're equal and they're like, yeah, it's got to be good math. All right, last thing. Every now and then I'll have somebody who'll try this mentality. Okay, I'm just going to grab one. Let's just say, down here. Okay, so every now and then I'll have somebody do this and they think they're really clever. And I'm sure somebody's pulled one over on me before, but they'll get to something like number 6 and they're like, okay, all right, I'm proving this one. If it's going to end up being true, I'm just going to start with that. And then they just write like a bunch of crap in here, play around, and they go, yeah, proved it. I'm a little bit better. You're not going to get away with that very much, if at all, okay? I'm really looking at your process. My key probably doesn't have anything on it when I'm grading your paper on these, because I literally am just looking at and following your work and going, is he doing something? But your goal, again, is to do something to this side so that it actually matches the right side, or do something to this side so it matches the left side. That's your goal. And if at any point you can do that, then you have proved the identity. Okay? So I want to see when you're doing this, remember, because the equal is like a question mark, we're just going to keep the left side. You're going to keep whatever you're doing to the left, you're just going to keep it on the left. Whatever you're doing to the right, you're going to keep it on the right, and you're just going to keep joining these. Every time you make a step, copy the other part down, put an equal. And your equals should stay right down the middle of the problem like that. We're not going to be working over to the right or working over to the left. Every time you do a step, write that step down, put an equal, copy the other part down. And since you're going to be like I am, sick and tired of copying the other part down, if I don't do anything to this, you're welcome to just ditto it as you're bringing it down. Okay? So let's just do some of these. We're going to start basic and we're going to start getting harder and harder. And hopefully you'll get these. And keep in mind, we're going to do this today. We're going to review tomorrow. We're going to review Monday. So we've got 3 days to absorb all this. And once you get it, I think you'll be in good shape. Okay? So here we go. Looking at this. Is this a true statement? I'm trying to prove it. Now, some of you might go, yeah, 1 equals 1. Well, that's not enough for me. It's true, but it's not enough for me because it is an identity, but you didn't prove that to me, okay? Now, sometimes you might go, well, Mr. Hurry, it's so obvious because any function times its reciprocal is always 1, and these are reciprocals. Then show me that identity. Are you with me? If in doubt, write it out. So right here, if they're reciprocals, show me that one of them is the reciprocal of the other. Cotangent, change it to 1 over tangent. And now I can see what you were thinking. Are you with me? And now it's pretty clear that those would cancel and I'd get 1 equal 1. Now that's enough. And you don't have to put a check mark. That's just me saying, oh, look, the left and the right are equal. Okay, moving up. And notice the equal sign staying down the middle. I'm just simplifying one side until it matches the other. All right, what about this? What could you do on number 2? And keep in mind, if it's on your identity sheet, it's already been proven, you can use it. These are both double angle cosine formulas, aren't they? Now, if you know your identities, you'll see that. You could go, oh, well, keep the equal. If that's cosine of 2 theta, and that's cosine of 2 theta, well, I'm done. I have proven, right? I worked with the left, then I stopped. I worked with the right. At any point, if they're equal, great. Now, if you were in Miss Rouleau's class, she would say, you can't work with both sides. You can only work with one side. Then you might have to do something like this. And again, not in my class. But if you were in a class like that, you might go, how can I change this to that? This doesn't even have a cosine. So what could I do with this cosine squared to change it into a sine squared? Are cosine squared and sine squared related? Yeah, what's cosine squared equal to? In terms of sine. I'm going to a Pythagorean identity. Is it cosine squared 1 minus sine squared? So I could replace that with 1 minus sine squared theta. Drop down this part. Keep the equal sign lined up. Just bring down the right. And now what's the left? 1 minus 2 sine squared theta. Oh, now they match. But in my class, I allow you to work with both sides, so you wouldn't even need to do this if you knew your identities, right? All right, what about 3 and 4? Check out number 3. And by the way, remember, you can use all the rules of simplifying. If you look at these and you're like, crud, I don't know what to do. I'm just going to change everything to sines and cosines. Maybe that'll help me see it better. That's an option. You know what? What is 1 minus tangent squared? Well, it's not an identity. 1 plus tangent squared is an identity. So how about this? I'm trying to make these match. So I either need to change the secant part into a tangent or this tangent part into a secant. Do you have any ideas of how to do that? What identity relates secant and tangent? And again, if you don't know your identities, you're dead. You what? Well, hold on. How does secant and tangent? What trig identity has a secant and a tangent in it?
Tangent squared plus 1.
Tangent squared plus 1 equals secant squared? So could I replace just this, not the negative, but just that with a 1 plus tangent squared? And then just drop down the rest? Can't I do that? Right? I'm replacing it with an identity, so it's still true. And then look, distribute the negative in. 2 minus 1 is 1 minus tan squared theta. Oh, look at that. They match. And as soon as they match, I'm good. Now, is this the only way to do it? Absolutely not. There's dozens of ways to do this, if not an infinite number. Although some would be very circuitous. What am I looking for? Circuitous. There's a word out there that sounds like that. It means to go around that. All right, what about this thing, number 4? Anything jump out at you? The 90 minus x jumps out at me too. That reminds me of one of those 90 minus theta identities. So what is the cosine, just out of curiosity, the cosine of 90 minus theta? That's the sine of theta? Okay, well, can I replace that then with the sine of theta and just drop down the cosecant and the equal on the 1? Now what? Anybody got any ideas?
Cosecant is 1 over sine.
Oh, and if cosecant is 1 over sine of x, oh, sorry, there's an x, not a theta. So keep that an x. At this point, you go, oh, the sine of x would cancel. 1 equals 1. And sure enough, this must be an identity. Because they match. All right, what about these next two? Now, in this one, that one on the left always gets people. They look at it and they're like, ooh, that's not attractive. Let's just take a look at it. Is this even an identity? Now, I look at the 1 plus sine theta, and that part matches, except this has a square root. Remember, I can't go and square both sides. Why can't I do that? This is not an equation. It's more like, is the left side equal to the right side? This is a question mark. Is it? So I can't do that. But what can I do? I'm going to play around with this left, and this is why. One, I don't know what the heck with this cosine right now, with the absolute value. I'm going to hope that that just happens. But if this is a binomial, is there a way to change a binomial into a monomial? It's actually one of the rules on your suggestions. We multiply by the conjugate on the bottom. And let's just see what happens. It's a thought, right? So I'm going to come over here. I'm going to put this square root out. This is what I currently have. 1 plus sine theta, 1 minus sine theta. And since it's under the radical, I'm going to leave everything under the radical. What if I multiply the top and the bottom by 1 plus sine theta? And I'm just going to ditto the right side. What do I get here? On the top, don't I have this? 1 plus sine theta quantity squared. And on the bottom I have 1 times 1. If I FOIL it out, don't I get this? Still all under the radical though, right? Is this right? What happens when I square root the top part? What happens when I square root an x squared? Do I get x? I don't get plus or minus. What do I get close though? Absolute value. If I square root this squared, okay, I would get kind of an absolute value, but hold on a second. I looked at it a little bit differently. I looked at this as the square root of 1 plus sine times the square root of 1 plus sine, and that gives me this, the square root of 1 plus sine squared. And if I think of it this way, the square root on the outside doesn't give me absolute value, does it? So I am able to just cancel it and get 1 plus sine theta. Now, I still have the square root on the bottom. I'm not doing anything to the right. Can I square root that? Sadly, no. Oh, but wait. What's 1 minus sine squared equal to? Cosine squared. And what is the square root of a cosine squared? Absolute value of cosine. Now, to me, this is one of the trickier ones. But I just wanted to show you, in fact, one of the really trickier ones. I just wanted to show you the idea on these. I'm looking at the right side. I knew I didn't want an absolute value there, so I was able to rethink this problem so that I wouldn't have absolute value, but I still needed it on the bottom because I ended up square rooting the whole thing, and that does give me absolute value. And when the left meets the right, I'm good. Number 6, a little bit easier. Anybody got any ideas? I'm trying to make them match, so I either need to get rid of this denominator or get a denominator here. Anybody got a suggestion? And remember, if you totally get stuck, what can you always do? Change the sines and cosines. Sometimes that helps. That'll at least get 2 functions as opposed to 4. So you said move the secant up? So if I move the secant up to the top, it becomes a cosine of x. Do you want to move the tangent too, or leave the tangent where it is, or what do you want to do? Okay, so if you're going to leave the tan on the bottom, that would be a sine over a cosine there. So I have a cosine x on the top because you move this up, and you change the tangent to a sine over cosine. You want to do anything over here? I mean, it looks like you're changing stuff to sines and cosines. You want to go ahead and make that a 1 over a sine? Just so everything's sines and cosines now? Now, give me something you can do. Because at this point, it kind of feels like we're just playing around trying to find something.
Cancel out the cosine x and just
You could if it was this, cosine x, sine x, cosine x. You see the difference? But this is on the bottom.
I mean, like,
No, if you break it up.
like, bring it, like, flip it and bring it up.
Okay, so to multiply by sine x, you do what? I mean, to divide by sine x over cosine x, you would do what? Multiply by cosine x over sine x? Ooh, that doesn't cancel. It actually makes it what? Cosine squared. I think we're getting somewhere though. Check it out. We get cosine squared x over sine x. Now here's why I say we're getting somewhere. I've got a denominator that's sine of x. Over here I have a denominator that's sine of x. So what would I have to do with these two numbers to combine them together to get one number with sine x on the bottom? Get a common denominator. That's one of the rules on my sheet. So I could put another sign under here on the bottom, but I would have to put another one on the top, right? Common denominator. What does that give me now? 1 minus sine squared over sine x? What's 1 minus sine squared?
Cosine.
Cosine squared x over sine x. And you just proved it. Now, I would argue you may have taken the long route, but that's okay. Nothing wrong with the long route. Certainly a way to go. All right, check it out. There's other ones that aren't as bad, some of them that are worse. Check out number 7. I'm looking at this and I'm like, how in the world can the reciprocal of tan and the reciprocal of cosine be equal to tangent plus cotangent? Well, what is 1 over tan? Cotangent? What's 1 over cotangent? Tangent? Well, that is what I have. And you don't have to rewrite it to change the order on an addition or a multiplication. The commutative property is obvious to anyone and approved, so we're good. What about this one? Is there anything that jumps out at you?
That's secant of the negative x.
So the negative x in there, those are the even odd identities. So when does the negative just go away? On the secant. So I can change that bottom part to just a secant. And what happens with the cosecant? The negative comes out. So I get a negative cosecant of x. Okay. Now, anybody got any ideas? Change it to sines and cosines? Okay, so a cotangent on the left, on the right, would be a cosine x over a sine x. And then what do you do with this secant and this cosecant? The secant u on the bottom is a what? Cosine u on the top. And the cosine, and I don't know why I'm using u. These should all be x's. And then the cosecant x on the top should be a sine x on the bottom. And look, you've made them match. And I didn't have to work on both. I didn't. Look, I could have left this negative cotangent from the start and then just said, oh, that's negative cotangent. But if you don't have the same thing on the left and the right, then you're not finished. Don't get to this. I have people all the time that look right here and they go, God, duh, Mr. Hurry, I don't need an extra line. That's true. How do I know that? You guys, some of you are still missing that identity on the quiz. Right? How do I know that you know that that's negative cotangent? You have to show. So until you have the left and the right side equal, you're not finished. Although you're fine if you want to just ditto it. To me, if it's unchanged, that's totally fine. All right, what about this one? Up in the game a little bit. You see anything that jumps out at you? Clearly, there's lots of secants and tangents. So I've got secant 6, parentheses, secant x tangent x, minus secant 4, parentheses, secant x tangent x. I have no idea why they decided to pull 6 secants out and not 7, or why they don't combine these two together, 4 and not 5. Why don't they just make it? I don't know. But is there anything you think you could potentially do here? And I would encourage you not to always jump on sines and cosines this early, especially when you've got secants and tangents, which are already related, right?
Did you distribute it and then?
Now, when you distribute, do you do this? Why not? Because it's times. So really all you're doing is saying secant 7 tangent x, secant 5 tangent x. See anything now? I think you should see it now. I'd love to, but I don't have like terms.
Oh, no.
How would they cancel? Because you can't divide them out. Rhymes with tractor. What if I factored out 5 of the secants, just to try it, and 1 of the tangents? I don't know why I wrote tax. Tangent x. 1 of the tangents, what would I have left here? Secant squared, what would I have left here? Minus 1. Ooh. What's secant squared minus 1? Tangent squared. That leaves me this. When I replace that with a tangent squared, and when I simplify, what do I get? Done. Now, I can tell you this. You probably, some of you are looking at these and going, well, how would you know to do that? How would I know? Well, maybe not the first time. But second time, these things need to start compiling in your head. And remember, you might have done this a different way and been fine. You could start with the right side. I mean, you could literally do stuff like this. Well, I'm going to change that tangent cubed into tangent squared tangent. And then I'm going to keep the secant to the fifth x and replace tangent squared with secant squared x minus 1. And then I'm going to take this and multiply it in, and this and multiply it in. And guess what? I can make it look like that if I want to go that route. Again, lots of different ways to do this. These are not fun to grade because I'm looking at each person as doing something individually. A lot of you will do it kind of the same way because there is a trend if you start feeling comfortable with the best scenario. But a lot of you are doing crazy things that end up being good. So what about number 10? Anything jump out at you? Cosecant and cotangent go together when they're squared. Huh. So how could I take the stuff on the left and get it to be a cotangent? You notice anything about that stuff on the left? Cosecant to the fourth, cosecant squared 1, it's a trinomial. What if I let cosecant squared equal a? What would I have here? A squared, what would I have here? Minus 2a plus 1. So what is that? What happens here? I got a perfect square trinomial. How would that have factored? A minus 1 squared. So couldn't you factor this right here as a minus 1 squared? Now, what's cosecant squared minus 1? Cotangent squared? Squared. And what's cotangent squared squared? Cotangent to the 4th. Now, did I have to do it that way? For those of you who are like, I'm not going to see that. No, check it out. Isn't cotangent to the 4th cotangent squared x cotangent squared x? And isn't cotangent squared x cosecant squared x minus 1? Cosecant squared x minus 1? And if you FOIL that out, don't you get cosecant 4th x minus 1 minus 1 minus 2 cosecant squared x plus 1? You can do it that way. Just be creative, and the more you see them, the better you're going to get on this. The more you skip these problems that are hard and don't ask questions about them, and a lot of times you'll look at your problem and you'll look at the book and you're like, I couldn't get anywhere. I didn't do anything like that. Come show me. The book is one of an infinite number of ways to get something done. You might be doing great things and made one small mistake. Come ask me about it in the morning. I mean, I'm here usually around 7:30. Today I was here at 7:15. I mean, come in here and ask me questions. Let me look at what you're doing. See what kind of progress you're making. The bell is about to ring on us. Give it a shot. Remember your rules for identities. Make sure your form is looking good. And we'll do more of this tomorrow and then more of it on Monday.